Okay, hi everyone. Sorry for the organization taking a little while. Yeah, it's great to be here and see all your faces. I still have some free spaces for people to like book in to talk to me before the end of the week because I'm here until the end of Friday this week. Okay. So today I want to talk to you about sample optimal classical shadows for pure states. This is joint work with my two awesome collaborators, Daniel Greer and Luke Schaefer.
Wow, that photo doesn't look photoshopped at all.
It's the only photo of Luke I could find on the internet.
So you said it's a mistake, all right? I kind of a patch up. It was not meant to be a joke.
Well, it is meant to be a joke. It's kind of a bit of everything. So these guys are at PI and IQC. Sorry, they're at IQC at the moment. They're at IQC at the moment, and I was at PI and IQC when I started this project, but since have obviously moved to this wonderful group here. Okay, and this is not an archive yet, but hopefully not too long. It's kind of we've presented it at TQC, so it's kind of close to the results are there. All right. So what this project is really about is learning quantum states, and the kind of main research question we want to ask in this setting is how many copies of a quantum state are needed in order to learn an approximate description of the state. Okay, so it's helpful to have this picture in mind. You have some a set from which a row can be chosen. So once a row is chosen, S-fold tensor product of row is prepared and set to some state learning algorithm that has to manipulate row, do some measurements, store some data, and in the end produce some row hat, which is some description of row. Yeah, some approximate description of row. So the way this is phrased is extremely general, and if you want to make progress in a question like this, you need to kind of nail down all of the choices. And there are a few. So one thing you might care about is what is the set of states from which this row was chosen? And there you might want to talk about maybe the Hilbert space dimension of the system. You might even want to have some guarantees on the rank of the system. Is it QR or is it arbitrary state? In addition, you might ask, are there any constraints on the learning? So in order to learn a quantum system, typically you have to do some kind of measurements on the system. And you might care about whether your measurements are independent or joint. So in the independent measurement setting, you might be motivated by, say, experimental considerations. So you care about like, your experimentals tell you that they can't measure many copies of the system all jointly, and so you want to like measure them one piece at a time. On the other hand, you might actually want to say, in the context of state learning, what is the limits of quantum mechanics, right? Like what is the set of stuff that I could do permitted by the laws of quantum mechanics that will kind of give me the maximum learning power? And in that setting, you kind of care about the joint measurement and not so much about the experimental motivations. Okay. Then I guess in terms of description, you might want to kind of nail down what you mean by description. Right. In particular, it's important for us that this row hat is defined by a classical description. So you want to learn some classical parameters that you can write down and make copies of that describe row hat.
But you're not saying anything about how many there are. There could be an exponential number of parameters.
Yes, that's right. And also the elephant in the room, what constitutes a good enough notion of approximation, right? How do you decide you've succeeded in your task of approximately learning row? And for that, many notions have been considered. So
Sorry to interrupt, but I mean, for state, you really mean this with the state, right? And not very specific expectation values.
I guess you could be a bit loose, in the definitions for now.
Oh, but I see. Sorry,
Yep.
Sorry.
So the kind of well-known example is tomography. And there what you care about is the closeness in trace norm. So in tomography, we want to make a statement like with high probability, rho hat has to be epsilon close to rho in trace normal. Yeah, and this is a very strong notion of learning. And so in this setting, in the joint measurement setting, it was known that d squared on epsilon squared copies are both necessary and sufficient in order to learn the state to this high level of accuracy. If we move to independent world, independent measurements, then we pick up an additional factor of d here. So we're going to teach on epsilon squared. Okay.
If you have sparsity guarantees, does the d reduce to like a sparsity factor or a rank factor?
I guess you're in like, are you in compressed sensing kind of world? Maybe that's a good question for Jens. I'm not sure, but I can tell you that if you have rank guarantees, then one of these D's becomes a R, the rank. Yeah. So I guess the key point here is that.
The question was like what the scaling is in compressed sensing? Or?
It's like if you say, okay, you have a rank R state, not like a arbitrary.
Yeah, I mean, the upside is, I mean, if you have
if it's rank R, then the D becomes an R.
But all of these become R's.
Just one of the D's becomes an R.
In compressed sensing, if you want to recover like a d-dimensional quantity, like d by d matrix, the scaling goes down from d squared to r d followed of d. From d squared to d. With an r in front of the r to the right. Okay.
And this is number of the states that you take.
So D here is like 2 to the n, where n is the number of qubits, which kind of goes on to the obvious point, right? That this thing scales really badly as soon as you have more than a handful of qubits, which is why people have kind of been interested in, well, you know, this is a very strong notion of learning. Can we, but it also gives us this very high kind of heavy cost to pay in terms of sample complexity. So can we move to a regime where we have much lower sample complexity, but we're still managing to learn enough about the state to do useful tasks, okay? And for that reason, people have started exploring all these other kind of methods. But the one I really want to concentrate on is this one here, which is a notion of closeness and expectation value, which is the notion of the Hakop Pashayan paper, and it's the notion that we're going to focus on now in this talk as well. So there, given some observable O, what you want is with high probability to produce some estimate of trace rho O such that it's epsilon close.
For fixed qubits. Like not system size.
So, I mean, for a row that you learn. So I haven't talked about complexity of procedure.
You use like fixed row.
Yeah, you've inputted a row, you've learned the state, you've done some procedure to learn it. And then what you want is to produce an expectation value estimate that is epsilon close to trace row O, which is the expectation value observable with respect to that unknown state row.
Can you comment more on the difference between 3 and 4? Because it seems that you can get 4 from 3 just by
yeah, I can, but like we've got like I've got like something like an hour for this talk, and if I go down the branches, like I want to kind of get to the end of the introduction, and I will talk about some basics. So I mean, but like I'm trying to kind of like focus on the most important stuff, right? I'm trying to present the most important stuff. So right now I can say maybe the key difference between these two things is obliviousness, right? But we haven't got like, I mean, no one else is going to be with us. So when I get to oblivious, I'll maybe comment, I'll come back to this and say, in contrast to the Aronson procedure. So I want to say that maybe this procedure doesn't work for just any O, right? But we kind of, the way Frankl and Prestel dealt with this is they actually say for any observable in some set of B, where B is like some positive real number between 1 and D, the dimension of the system, and this B somehow grades the set of observables, where when B is small, you get a small set of observables, and as B gets bigger and bigger, the set of observables grows. And the reason they chose the gradient they chose is because somehow the sample complexity of achieving this task scales in this gradient B. So in particular that they show for independent measurements, B on epsilon squared copies are both necessary and sufficient. for achieving this task. So the complexity depends on the class of observables you're considering, and somehow as you grow this class, the complexity grows, and this B is the kind of right way of looking at the set of observables.
I'm meant to think of this as like a generalization of rank.
What? The rank?
Of the rank.
Yeah, that is a good way to think of it, but you won't know yet, because in the next slide, I'll kind of talk about what OBS actually is, but right now I'm just trying to give you a feel for what the procedure is and what this result is, HKP. Okay, so I want to kind of dig into this a little bit more. So let's try to understand the HKP setting. Okay, so first of all, the set of states, or this family here, could be mixed or pure in that setting. So they don't have a guarantee on the purity of the state. And also, these measurements here are independent measurements. So they're kind of motivated by these like experimental considerations. And just as some terminology, this output here is known as the classical shadow. And of course, the notion of approximation is this closeness and expectation value. And so what they say is, for all observables in this set OBS B with high probability, the estimate produced will be epsilon close to the true expectation value. And here, this with high probability is with reference to the randomness in the procedure that produces rho hat. Okay, so when the state learner gets these copies, they have to do some measurements in order to extract some information, and there's some randomness in those measurements. And so, always those measurements could get really unlucky and not be representative of the state we're measuring. And so there's some probability of failure associated with that. That's what this is in reference to. And another kind of key thing is that this procedure is oblivious. And what that means is that the procedure by which you produce this rho hat is independent of the O's that you're going to be dealing with later, right? So when you do this procedure and you learn the state, you don't yet know what O's you care about, right? Except for some general statement about some big class that they might live in. So in this sense, I mean, this ties into what the question you just raised and what you said earlier, which is like somehow obliviousness is kind of gives you more of a notion of learning than the Aronson procedure, which is not oblivious. So in the Aronson procedure, one tailors the measurements to the observables that you care about. And so you're kind of not really learning the state, but you're learning some properties of the state that are of interest in the Aronson procedure. Whereas here, you're really like, you don't know what properties are of interest yet, but you're trying to learn like the state more generally. I mean, you have some idea, like you care about expectation values and maybe for some large set, but this set is very large, so it's somewhat a general task. So to give you a feel, I should maybe first say, this F thing, it looks kind of complicated, but it's actually quite simple. It's what in the simplest case, what you might expect is that this thing is just trace rho hat O, and it's almost that. So in fact, what you do is you produce a bunch of rho hats that are independently produced, and then you compute a trace rho hat O for each of them, right? Which gives you a bunch of independent estimates of the expectation value. And then you take the median one. So rather than averaging them or something, you take the median. And this trick is called the median of means. And the reason you take the median and not the average is because somehow the failure probability, this with high probability, that failure probability gets suppressed exponentially in the number of terms you have that you take the median LPR. So it's a nice trick to use, but also somehow this is a general trick that sits at the end of like all of these cool arguments that you do in all these kinds of proofs. And it's kind of really, all the interesting stuff happens before this. So the real goal is to get each of these estimates to be good enough in the first place. So just get each of these to only fail with some constant probability. That's less than 1. Yeah, once you do that, then the median of means can be applied and exponentially suppress that value probability. So for the rest of this talk, I'm going to kind of ignore this median of means trick altogether and just imagine that you just have one rho hat instead of a bunch of independent rho hats. Okay, and finally, I want to talk about what this set OBS is. So it's a set of observables, so the Hermitian, and their eigenvalues are bounded between -1 and 1. and we require that the trace O squared is less than B. So this trace O squared less than B is kind of this gradient, right, that I talked about earlier. It's a thing that we have there because the complexity, the sample complexity depends on it. On the other hand, this normalization condition that the eigenvalues between -1 and 1 is kind of there to stop you from cheating or to make any kind of statement of a theorem possible, because without kind of a condition on the normalization, what one might be able to do is take your observable, multiply it by 1,000, and now you get like an observable with big eigenvalues. And if you had a theorem that said you could compute expectation values to additive error epsilon, then you do that, and then now you divide it by 1,000, and now you have an epsilon on 1,000 accuracy estimate of the expectation values. And obviously you shouldn't be able to do that. So there's like a limit on the normalization for the theorems to be true. It's kind of a technical thing anyway. But I want to maybe give you a feel for this thing, like what is this set of observables, and show you that it's actually quite rich. Note that for B equals 1, so this set obs 1 already contains a set of all density states. It's easy to check, obviously, because trace rho squared is less than or equal to 1. But that's already a pretty rich kind of set. So if you wanted to do trace overlaps with lots of states, then you could do it and pay a very small cost because these are the ones.
So that would be the observable is the rho is observable to compute the trace overlap.
Yes. Yeah. If you wanted to consider projectors of rank R, then you need to move to B equals R. And somehow Pauli's are the worst case setting for this, because all Pauli's live in obs 2 to the n and not obs 2 to the n minus 1. There's the square root of Pauli's identity, and if you take the trace, you get the dimension of the system. And so when you look at this scaling, in light of this, you know that computing trace overlaps is really cheap. It's just like 1 on epsilon sample complexity. But if you want to compute expectation values with respect to all these Pauli's, then you need to pay a factor of D here on top of your inverse epsilon squared.
D being 2, yeah.
D being 2 there. Yeah, dimension of, D is always the dimension of the row.
Mm-hmm.
Yeah. Okay.
But string operators and so are completely included.
Yeah. Yeah, and it doesn't matter, the weight doesn't matter in this setting.
Exactly, that's my point. When we discussed earlier, like an X string all through the system, it's perfectly included.
Yes, but I mean perfectly included when you sample complexity is 2 to the n divided by z squared.
Yeah, okay, sure. Okay, yeah.
Okay, so this is the setting for this talk is as follows. So we still, of course, care about closeness and expectation value as our measure. But we're going to restrict ourselves to pure states. Yeah, so we have a promised state is pure, and in principle, we now know more about the state than we did before, because before it could be mixed altogether. And so, in principle, it's feasible that we will have a lower sample complexity because we know a little bit more about the state. In addition, we're going to consider the setting of joint measurements, and there we have more powerful access to the quantum information. We can do more general measurements. And so again, in principle, we can learn more from the state. And so we want to kind of see how does this impact sample complexity? Can we do far better at a lower cost if we had that access? And also, what are the limits of quantum mechanics in probing this information? And so the main kind of outline of this talk is first, we show a sample complexity upper bound. How many samples do we are sufficient? And then we show a sample complexity lower bound, how many samples are necessary. And then we'll discuss some open questions. And so a spoiler is, this is the sample complexity upper bound. So we say that these tildes hide log factors, but the number of samples that is sufficient is the maximum of these two components. There's an inverse epsilon squared, and then there's a square root beyond epsilon component. And we'll have a lower bound that exactly matches. So it's again a maximum of these two components. And just to contrast this with the HKP setting, we see that if we're in this first world where this was the maximum, which is kind of at least the interesting, the hard parts of the proof here. We'll see that we get a square root improvement on HKP. On the other hand, if we're sitting in this regime, then we get a vector improvement.
See, but to be sure, the only assumption we do on the states are that they're pure. There's no further structural assumption, right?
That's right. Okay. Yeah, we've just changed two things. States are pure and then it's going. Yeah. You go first, Mark.
Okay. Yeah, like my question is, like, do you explicitly in your results assume that the party measuring doesn't know the measurements beforehand? Like, do you make use of this obliviousness?
Yes.
So these are results, like, if I were to know which observables I wanted to measure, would these bounds still be true?
So the Aronson procedure is better than our lower bound. Yeah. So if our lower bound didn't use that, you know.
But how do you incorporate that? Like, I don't.
Are you asking me how we show the lower bound?
Like how, like even in principle, how can you get this into the? I don't understand how you write down the theorem in that case.
We're about to see it.
Okay.
So maybe we'll talk about it after.
Okay.
Kind of picture. All right. So we're about to like get into the actual like hard stuff. So all of this for setting up. So if there's like questions about the setup or something's unclear, then now's the time to. Sorry, Johannes, you had a question as well.
I was just like, I wanted to ask, like, if there is like an rank R equals 1 factor that is probably in there somewhere. So if you scale up to like rank 2 states, that would be like 2 if you're in some place or something.
Oh, that's a good question. Like, is there a assembly mindset?
Yeah.
Yeah, you mean like these B's might be R's. I mean, these B's are kind of up. Yeah, these B's are upper bounded by the ranks of the observables that you deal with.
I mean, of the state.
Yeah, but yeah, there's no kind of rank assumptions of the state. I mean, the state is assumed to be R equals 1 here, but not in here.
No.
Yeah, so the question is,
the equivalence of norms say if you have a rank constraint, then of course you get these prefactors and the equivalence of norms that are dependent. It's a bit like that, right? You know,
I mean, that's something expected. If you did an analysis for like a rank R states and not rank 1 states, then you get like OR times something.
Yeah, to be honest, I mean, we can have a more educated discussion about this afterwards because you'll see what our measurements are and stuff. But I get the feeling that like the joint measurements are a huge component of the savings. It's not clear to me what the state rank restriction is in terms of savings here, but we should maybe have a discussion about this after. Yeah.
You know, another question. In the first classification paper, they show that with not clear knowledge about the observables, the sample complexity single copy measurement is optimal. But do you have also an optimal results for quantum memory accepting?
Yeah. So I mean, this is the fact that the lower bound and the upper bound match means that, I mean, the upper bound says like there exists an algorithm that can achieve this, and the lower bound says no algorithm could do better than this. Yeah, and they're the same, which means the algorithm is optimal.
This depends by the specific measurements that you do, or
no. In general, there's no algorithm that solves this task that I've presented faster than the algorithm we're going to show you.
Okay.
So when I show you the upper bounds, we'll be using like group theoretic kind of
the lower one matches the upper bound. So
yeah,
in this sense,
that's right.
To prefactors, it's so rare.
And so I want to kind of get through both of these. Each one's going to be about 20 minutes of talking. But this stuff here is like, you know, group theoretic harm measure type tools. And this stuff here is like complexity theory, information theory type tools, like reductions and stuff. So they're very different methods. And it's kind of amazing that they give you the same answer in the end. But I'd like to kind of show you. So if you guys are ready, let's, okay.
Yeah. Nice. I'm probably at the back. So I'm not sure I completely understand this median procedure. Like, how significantly would your bounds change if you were to do an average? Just intuitive.
Okay. What will happen is your failure probability will decay polynomially instead of exponentially. So if I tell you like, you know, you can do this procedure and there's a 10% chance that the procedure fails and 9% time it's great, and then you want to do it like 10 times, how much better will it be? Well, it'll go from 10% to 1%, whereas it could have gone from 10% to 1 on 10 to the power of 10. Yeah, it could have been like really suppressed. And so you should use measurements.
Okay, just one more from me. Like, can you actually disentangle the assumption pure state and joint measurement?
No.
No.
But I mean, this is what we have at the moment. In the open questions, I'll talk about the possibility of disentangling.
Okay.
That's an open question.
To come back, I mean, as you said only once, but to come back to your honest point, I mean, so in the joint measurements, you really need that you have the same row to the power n. Because, like, for example, row 92, we would have like rho, sigma, rho, and so on. I mean, you could have made 32 terms that with different states at different positions, but you really have the same guy. It's like sure by
I mean,
yeah,
the assumption.
We maybe shut up and ask this later.
Sorry, I mean, I guess you're saying how robust is it to like perturbations of this thing, right?
No, I mean,
it's not necessarily
rank 1 of the state. In the row to the top end, you have
you end up with a full rank. But the thing is, I mean, it could be that they're not tensor products, but they are all rank 1, and then the tensor product is rank 1.
No, but
I mean, sorry, they're not exact
state is like 1/2 rho plus 1/2 sigma. If you expand that, you get all
then you get full
rank.
But in principle, it could be like sigma 1, tensor sigma 2, tensor sigma 3, and each one is a slight unitary on the other or something. Yeah. Okay, all right, let's get into the hard stuff, okay? So the statement of the upper bound is given this many copies of an unknown pure state, there is a joint measurement that can be used to construct a classical shadow rho hat such that for all these observables with high probability, the expectation value estimate is epsilon close to the real expectation value. Okay. So I want to point out what this statement is not saying. Maybe I should say that it's important, the order of these quantifiers. We say for all observables in this thing with high probability, something happens. And we don't say with high probability for all observables, something happens. Yeah. The latter would imply something like with high probability, the supremum of the difference over all of the observables is small. Yeah. And we're not saying that. What we're saying is for all observables in the set, pick one, whichever one you like, it'll be true that with high probability, the expectation value is good. Yeah. And yeah, the key is kind of like rho hat and rho might actually be far from each other in trace distance, right? But O, if you think of O as like a projector or something, only projects these onto some subspace and then looks at the distance between them. And you're saying that with high probability, when you project, the distance between rho hat and rho will be close. Yeah, but you're not saying that it's always close, because then a statement like this would violate the no lower bounds from the Yeah, it's like a key.
Okay, for all of it, that would be just trace distance, right?
Yeah. And I should say that the measurement that we use to prove this can be implemented with an S+2 design, and we can also show that it's going to be a high design. So it's going to be like square root B design or something. So it's kind of very non-trivial measures that we've got to do to get this kind of sample. But if you don't know what that means, don't worry about it. You can just ignore that. So maybe the next thing I want to do before I even like prove this or kind of argue how we show this is first tell you what is the procedure by which you generate rho hat. Okay.
Here the number of elements in your sample and the polynomial in the sample complexity.
The number of elements in what?
In the
In the set of observables. Ah, yeah. Okay, that's a good question. So it ends up being a log in the number of observables you care about, because this with high probability thing can be exponentially suppressed, and so you could handle exponentially many observables, each one exponentially suppressed, union bound them, and still get something that's exponentially small value probability. Yes. Okay, so this is going to be the method for the construction of rho hat. Okay, so the first thing we're going to do is we're going to measure this S-fold tensor product, and the measurement we're going to use is the following POV. It's going to have two components: a psi component and a rest component. Okay, so this rest component is a single outcome. It's just like rest, the one thing that happens. Whereas this A psi has lots of POVM elements in it. It has, in fact, a continuum of POVM elements, okay? One for every state psi, okay? The set of A psis, each A psi looks like this. It's an S-fold tensor product of some pure state psi. D mu, this is like the Haar measure, and it's there because we have a continuum of POVM elements. And this is just some positive constant, just a normalization constant. Okay, so we have this like weird POVM measurement we're going to do, and it's going to turn out that when you take your state rho, if it's a rho tensor S, it's an S-fold tensor product of pure state, then you will never see the rest outcome. You will always see something in this A psi, which then means you will see some state like this appear. Like some psi will be the outcome of doing this measurement.
But that already explains that my rank 2 product will not work. Because then you always end up in, or the type already end up in the rest.
Exactly. Which is one of the limits of one of the things we need to extend if we want to move to dynamic states. Yeah. Okay, so I've told you what the measurement is. I'm going to tell you what you then do with this psi that you find when you do this measurement. So once you get your psi as an outcome, you just do this linear transformation on it. Times it by something, minus the identity, divide by S, and your rho hat is this thing. That's your estimate of the state now. It's a weird estimate because you will note that we're trying to estimate some pure state rho, but what we get is far from a pure state. In fact, it's not even positive. But it doesn't matter because this rho hat is going to be, have the magic that gives you this property and satisfies this theorem. It's going to be really good for computing expectation values. Okay, so before I go on to like trying to argue why this theorem is true, I also want to, as a first warm up, I want to show you that this POVM is a valid POVM. Okay, which means that all of the elements should be positive and it should integrate to 1. Yeah. So let's do that. It's pretty clear that these A psis are positive because that's a positive state. It's the Haar measure mu, and this is a positive constant. So that's all positive, but let's integrate these A psis because of course the natural definition is to define rest as I minus the integral of the A psis, and you want to kind of know what the integral of the A psis is in the first place. So let's take this integral of the A psi. I've divided out this kappa S, and that's what it looks like. It's an integral over the Haar measure of psi tensor S times. And you might be familiar with this object. It's known as the moment operator. It's like the Kate moment operator where K equals S. And it's got a name, NS. And so if you've never seen how this integral gets done, I think it's like a cute little exercise in group theory that's like really nice. So I'm going to go through it. It's going to be a couple of minutes. So to do this integral, you first know that this thing has a big commutant. So in particular, I take any unitary U that acts on the space of psis or rhos. You take S-fold product of U, and this thing will commute with this operator. So to see it, you can try to conjugate it with this U, and of course the U will act on each of these psis and increments of psi dash, and you can just get a psi dash tensor S times, and then you're integrating with respect to the Haar measure, which is unitary invariant. So it's going to integrate to the same thing, and so it has this comment, right? And then Shor-Weil duality tells us anything that has a commutant with this group can be written as a sum of permutation matrices acting on the space. Where these are the permutation matrices, these are the coefficients. Then we also know that if you take some permutation matrix that permutes S objects and you act from the left on MS, what that's going to do here is going to go into the integral. It's going to permute these kets without touching the bras. But the kets are all the same, so it's not going to do anything. On the other hand, if you acted with this permutation matrix on something of this form, we see that these coefficients get permuted around. So to get back the same thing for every permutation, these coefficients must all be the same. Yeah. So then you know that this moment operator is actually the average, like proportional to the average of all permutations, which goes by another name. It's the projector of the symmetric subspace of the subjects. Okay, nice. And now the only other thing we need to know about this is the normalization. So take the trace of both things, right? You take the trace of this, you're going to get one integrated over the R measure, and R measure integrates one. So, you know, this integral, and the trace of this is one. But on the other hand, if you take the trace of project onto a symmetric subspace, you get the dimension of the symmetric subspace. So that tells you the constant of proportionality is this kappa S, which we define as the dimension. Okay, and now we know that this thing, you know, what this operator is. And so we know that this thing integrates to the projector onto the symmetric subspace. And so the rest must be I minus the projector on the symmetric subspace. And that's very nice because I minus the projector is positive. And so we're done. The sum to the identity of every element is positive. Okay, so that's a valid POD. If you want to know how to actually implement the measurement, I can delay this to the end of the talk and then dodge it then. All right, and also maybe you can see that S-fold tensor product of any pure state is going to always kind of give an answer in one of these A sides because it lives in symmetric subspace. Okay, now we're going to go on to the proof. Okay, so it's going to be two steps: an expectation value computation and a variance computation. So in the expectation value computation, we want to show that like the average of that on the expectation value of our estimator is the thing we want to estimate. So it's unbiased. And in fact, we're going to show something a bit stronger. We're going to show the expectation value of rho hat is rho. Yeah.
In other words, the choice of observer is not entering yet.
Absolutely independent of the observable. Yes. Right? It's absolutely independent of the observable, but it wouldn't, I mean, this wouldn't imply, if this was in general true for all observables, but this property not true, I mean, actually, I don't even know if that's possible. So, okay, I agree.
Because I mean, of course, there are settings where this is not the case. I mean, that's for things that are true in the ground space manifold, and they always kind of are basically proving that. Then, of course, you can have a not a faithful estimator while still having the right thing on that.
If the O's are sufficiently rich, then exactly. and you have this form of the estimator like being
for a product base, for an operator basis, that's the same.
Yeah.
That's right.
Okay, so the first thing you want is like unbiasedness, so the expectation value is good. And then the second thing you want is the variance is small around that expectation value, and then you have a nice estimator. Okay, so what we want to show is that the variance of this guy is something like some small constant times epsilon squared. And then we'll be like in a good place, because once we have this, we can apply Chebyshev inequality and meaning of means, and everything is just easy. Yeah, this is the hard part. Okay, so let's get, we're going to look at the expectation value and then we're going to wave our hands for the variance, because it's a very similar calculation. But before we do, let's recall that rho hat was just a linear function of this psi guy. So if you want to compute the expectation value of rho hat, then you need to compute the expectation value of psi, and then everything is easy. Yeah. So let's compute the expectation value of the psi guy, which is the measurement outcome when you do this measurement, right? Okay, so the first line is plugged in the definition of expectation value. Expectation value is something times the probability of seeing it happen. And this was the POVM measurement, right? That's the state we're measuring. That's the probability. And then to go from here to this line here is like basic arithmetic. It might seem a little bit complicated because the form is a bit different, but it's very easy. So let me just say, recall that this A psi guy had like an S-fold product of size in it. Yeah. And we're going to add one more to it, and we're going to get an S plus one-fold product of size. And then we're going to integrate that. So the integral is going to come into trace and do the integral, and you're going to get a projector on the symmetric subspace. But you know, this trace was on all of these guys and not on this first side. So now our trace is like on all but the first element. So what we've done here is like we've taken the trace out, put the integral on the S plus one-fold tensor product of sides. That's all that's happened here. And we picked up like an I in front of our S-fold product of rows. Because this I doesn't get traced. But anyway, this is basic arithmetic. And then getting from here to this line here is kind of the fun stuff. And I'm going to try to kind of show you how the fun stuff goes. It's helpful to have this picture in mind. So what we have here inside the trace is like this product, S-fold product of rows. I've written as like a tensor network type picture, tensor with some identity. We can think of this as a matrix. There's some like domains, and then the matrix applies, and there's a codomain out here. And then we're going to multiply it by this other matrix. And of course, this has a domain and a codomain. So the domain up here is going to act on the codomain of these guys for this matrix multiplication. And it's going to be useful to remember what this projector on this matrix size basis is the average of permutations. But let's kind of see what this looks like. So writing this in that picture we saw, now these permutations act as permutations on the codomain, right? And we get stuff out the bottom, and we're averaging over all permutations. I'm going to split this permutation over S+1 objects into a permutation over S objects, and there's going to be two pieces to it. So the first piece is where the permutation fixes the first thing. So it sends 1 to 1, and then it can do anything on the rest. And the second piece is when it sends 1 to something else, and then picks one of these guys to send to 1. There's S ways to pick one of these guys, and they're all the same because they're all the same. So we get S times, like send the second guy to the first guy, and then do anything you want on the rest. And now we're only summing over S-fold permutations. Okay. Now what? So we've done we've just done some pictures now. Now what? We want to take the trace of everything but the first guy. Yeah, and you might remember from kindergarten, taking a trace is doing this, right? The codomain gets wrapped to the domain.
We installed and proved in our house.
So we've got to evaluate this thing. Okay, how do we evaluate these weird diagrams? It's having like a nice little example is kind of very educational here. So imagine you have three guys A, B, and C, and you want to apply the identity permutation to it, and then take the trace. What does that look like? Well, it's obvious. It's trace A times trace B times trace C, right? Let's do something a little bit more interesting. Let's apply a swap on the first two guys. What happens? So you have you start here, and then A acts on it, right? And then it goes out, and it goes and wraps around to the domain of B. So then B acts on it, and then the codomain of this guy wraps around back to the domain of A. Yeah, so it looks like A acted first, and then B acted. And then you took the trace because you wrapped it back around. And of course, nothing happens to C. It just gets a trace C. If we go to the 3 cycle here, then again, we start here in the domain of A, and then A acts. And then we wrap around, and we go to the domain of B, and B acts on it. We wrap around, domain of C, C acts on it. And then we go back to the domain of A. Yeah, and so you get A times B times C trace. Okay, so maybe you're getting kind of a feel for this. So every permutation element sigma splits into a product of cycles, and each of these cycles has like some degree, and the number of so each of these cycles is going to correspond to a trace, and there's going to be a product of matrices in there that correspond to the degree of the elements. All right, so let's try to use this intuition in here. Note here that we're going to get a product of cycles for the sigma, right? It's going to be like trace of some cycle, but all these cycles are going to be just rows. Yeah, so we're going to get like row times row times row, as many rows as there is a degree in that cycle. So we get some power of row here trace times some power of row here trace, and so on, right? But row is pure, so power of row is just row. And the trace of the state is just 1. So you get 1 times 1 times 1 times 1, right? And the only thing left over is this identity that wasn't traced out. And so the identity stays there. So you just get this whole thing for any permutation of sigma just collapses with identity. Right? That's very nice. And if we look here, we're going to get some leg come out here that's got a row on it, but it might have more rows on it because there's more cycles in here. So we get some power of a row coming out. And then everything else is like a bunch of cycles of rows. So we get like trace some power of row times blah, 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 right? And again, state is pure. So all of these trace terms are one. And we get some power of rho, which is just rho. So this whole thing just is going to simplify for every permutation to identity plus S times rho. So like maximal simplification, right? Like, very nice. And then and we're pretty much done. And now we have to like say, oh well, what was the expectation value of rho hat? Well, we're going to choose the definition of rho hat exactly so that its expectation value becomes rho, because it's pretty easy to do that, right? It's got this linear form. So psi is linear with rho, and we want a linear function psi that will return rho. Okay, so we've got unbiasedness now. And if we want to compute variance, then we're going to have like terms like psi tensor 2, we're going to take expectation values of, and we're going to play the same game. There's going to be more counting. It's going to be a bit harder to count and decompose things, but you're going to use much the same mathematics, and after a while, you're going to get some answer. And it's going to be like this, right? And I think there's a nice conceptual thing to get out of this equation here, which is if you look at the variance of like some estimator, and it's like V, and then you try to do it a bunch of times independently, say you did it K times independently, and then average them, then the variance of this average is going to be like V on K. You can get a linear decay in the number of terms that you're independently averaging. And we see that linear here, linear component here, except it doesn't have the V bit. Somehow the constant variance component is like one, it doesn't really depend on the problem, the properties of the problem. There's another piece that does depend on the properties of the problem, like this trace O squared. Somehow the hardness of O matters, but that component decays quadratically, and that's the number of samples, not linearly. So you're getting a faster decay of your variance in the number of samples, which means you can use less samples. And that's where we're getting this quadratic speed up on crystal. And I think this is due to the joint measurements that it's hard to disentangle the two, because it was critical that the powers of the rows to be low.
Something is not so clear to me. Can you show your post-processing state, your show state?
The definition of row hat?
Yes, exactly.
This thing here?
Okay, this you save in classical memory. You save
you save the size. Yeah, I mean you could save the size in classical memory, and then you automatically know how to make for a hat. Yes. But there's only one side. I mean,
what's that?
There's only one side because it's like a joint measurement.
But it's
a continuous state.
No. I mean, it's can be exponentially that,
That's not the point, I think, of this work. I think this work is not about practicality at all.
But I mean, it doesn't have to be exponential large. So, I mean, the way I've written it here and the way I've presented it's like a continuous measurement. In reality, you could do S+2 design, which would discretize your space of states, and then you could do like discrete measurement. So if you figure out how to do like a measurement based on an S+2 design ensemble, then you will have like some like it won't be a continuum, so you'll have some finite bit string that represents your psi. And I believe that finite bit string will be polynomial. Because S+2 design, if S is polynomial, then you only need like n squared times t to the 4 for like t design, right? So you're right.
Okay, I didn't get the points. But because the point of the speciality is that your unbiased estimator is efficiently storable. Here you don't store that.
Yeah, you can store it. You can store your psi efficient. If you could figure out how to do the measurement that will give you the psi, then you can store it. Yeah. Yeah, you just have to. I mean, right now I'm presenting it as a continuous measurement, but it doesn't have to be. It could be a measurement that's discretization of the open space.
But then again, you can use an S+1 design or something.
Yeah. Yeah, we need
So
to.
it's really continuous. I mean,
Yeah, but I mean it's finite, and it's the number of bits you will need to store it will be polynomial in the sample.
that from the Komoro complexity perspective, but it would not be make a big practical difference.
Oh yeah, I mean this is not a practical project. This is about I mean
I'm not critical. I'm just
I guess that if I understand correctly, like the bottleneck with rho non-pure is that you don't get such a nice closed form for this inverse channel, right? Or even for this measurement channel. But could you still potentially
as soon as rho is non-pure, then you can get the rest outcome. Yeah, and there's and right now we just lump it all into rest because we don't care. But if rho is non-pure, you get the rest outcome a lot, and you might want to fine grain all of those outcomes into something that's informative. Right now we don't care; it's just some lump that we'll never get.
Okay.
Yeah, and it's like a whole kind of project. To, we've thought about this and tried to like work on it, but it's not trivial. Like you have to work hard.
You have to change the measurement, right?
Well, I mean, I guess you'd be changing the measurement by fine graining the rest guide. Yeah.
I don't think because I think that take road to the S. I mean, this will also be better for them, right?
I would be very impressed if anyone in this room can a solution to this. Like, I mean, it's not easy.
it's pretty crazy. I mean,
Yeah.
It's difficult enough for the modern form.
Yeah.
Okay, but again, I mean, it's like purity and go to the power n measurements. That's kind of the part. Okay.
All right. So if you were tired with representation theory, group theory stuff, it's time to wake up and celebrate. Okay, we're done with that. And now we're going to do like reductions and information theory and stuff like this.
Research from cute dance.
Yes.
Downs.
All right. Here we go. Enough with the cuteness. Okay. So the statement of this sample complexity lower bound is that we need at least these many copies of some unknown state rho to construct a classical shadow such that for all observables with high probability, this thing. Yeah. Okay. Okay. It's worth noting that like there's two components to this lower bound. But because the lower bound, we have one lower bound for this component and one lower bound for this component. And they both apply, so the maximum applies. Yeah, and what I'm going to show you is just this one piece here, because it's kind of the one interesting piece, I think. And this is the key, there's like four kind of key ideas in this proof. So one is I'm going to introduce a thing called the partial matching problem, which is a communication task between an Alice and a Bob. And this procedure has been studied, and there's a known lower bound in the amount of communication between Alice and Bob in order to achieve this task. Then I will show a reduction from this partial matching problem to our problem of expectation value estimation, which will then mean somehow we'll have to set up Alice and Bob in the expectation value setting, and we'll show that there's some minimum amount of communication that Alice has to send to Bob in order for them to achieve the task, which is going to be associated with the expectation values. Then we're going to like somehow lift this lower bound on the amount of bits that Alice has to send to Bob to a lower bound on the amount of information that Alice sends to Bob with respect to some other variable that's unknown. And then finally we're going to kind of piece this all together, use like Levo's theorem and data processing inequality and stuff to like get the whole lower bound. Okay, so I don't expect this all to make sense at this stage, but like gives you a feel for like how the pieces are going to fit. All right, so let's get started with this partial matching problem. This is courtesy of Davinsky, Kemp, Kurnavis, Raz, and DeWolf. I just say Davinsky et al, but now I have to read it because it's not the okay, so in this, there's going to be an Alice and a Bob. And Alice and Bob are going to get some data, and it's going to be helpful for you to think of Alice having some number of vertices and Bob having the same vertices, just for you to attach the data to it, like for pedagogical reasons. Okay, they don't actually have these vertices. The vertices don't need to be there at all, but it's going to be helpful for you. So just imagine that they have vertices. what Alice and Bob actually get as data is the following. So Alice is going to get some bit string of length B, zeros and ones. And it's going to be, it'll be useful to think of these as bit assignments to the vertices that Alice has. Bob is going to get a thing called the partial matching, which is going to be pairs of numbers, right? You can think of them as pairs of vertices. And there's going to be epsilon v of them. So some fraction of vertices is going to have an edge attached to it. So you can think of these as edges on your vertices. The only condition is that any vertex can't have more than one edge attached to it. You can have 0 edges or 1 edge, but you can't have 2 or more. So this is the partial matching data, some edges. But in addition, Bob's going to get some bit string. And you can think of this as attaching a bit to each of the edges. This bit string is the same length as the edges. And so you think of it as a bit assignment to each of these edges. And now there is a promise. And the promise is that for any edge you pick, the parity of the vertices possessed by Alice, plus the bit assignment on that edge possessed by Bob is a constant. It's some b. B could be 0 or 1. You don't know to start with, but you know it's the same for every edge you choose. Yeah. So let's look at an example. So, well, before we do, maybe Alice can send a message to Bob, a single message, and the goal is to figure out what B is. And the question is, how many bits must Alice send to Bob such that we can learn B? So if Alice sends the wrong bits, Bob can't learn B. If Alice sends a pair of bits that collide on an edge, then Bob already knows this, so it can be like the parity was 0 plus the slung guy value is 1, right? I know B is 1. And it wouldn't matter if it was this edge or this edge, because of course, on this edge, the parity is 1 plus the 0, it's 1 again, B is 1 again. Yeah. All right, is this clear? Mm-hmm. Okay, great.
Okay, this is one-way communication.
One-way communication, yeah. Okay. All right, and so the result of Gubinsky et al. Was that the maximum message length must be greater than square root beyond epsilon for Bob to run the secret bit for a high fraction of instances.
What is this for? What is it? For a high fraction of instances.
Yeah.
Sorry, what is it?
I accident.
Sorry? You're saying that, like, for the optimal communication strategy, the longest message has to be at least this.
I also don't understand why the longest message.
That's just that's what they can prove. I mean, if they could prove that the shortest message is the average message, it'd be really helpful. What's that?
The longest message over the set of parties, right?
Yeah, it's like over the set of all, like whatever strategy Alice and Bob choose, right? However good it is. If you look at that strategy and you check over all the X's and whatever that they could receive, what is the longest message that they would have to send? It will always be more than this.
Yeah, this sounds like completely unuseful. It still doesn't make sense to me. Like,
well,
would you want the
shortest
message? Yeah.
No, I think this is the longest, shortest message. So it's like maximum.
It's the longest message of the optimal procedure, not just the longest message of any procedure. Like you want to, it's a lower bound, right? So you want to say like in the best case, you will never get a
max min now, yeah. Okay.
All right.
Sorry, I don't understand. But like by the longest, like isn't a message just Alice sending a string of bits?
Yeah, but in principle, Alice could send the longest string of bits depending on the X value. So it could be like, you know, send only one bit if your X is all zeros. Send, you know. Okay, so we're gonna now talk about a reduction from partial matching to that's a this thing. It's the expectation value problem, right? I should probably just say this terminology is a bit confusing. So when I say reduction, it means that this problem here on the right is harder than this problem on the left. Yeah. So a reduction means that, what's that? I can, but it'll go somewhere else that's going to block something else. This is like.
It wasn't there before. Just click on the slide.
Click on the slide.
Oh, the chat message.
Oh, is there a message? Okay, let's read the chat message.
Oh.
Okay, no worries. That's fair enough. Okay, great.
It's all two problems in one shot.
All right, so this is the hard problem. This is the easier problem. What we really are saying here is like, imagine there was an oracle for solving this problem. Then automatically that would be able to solve this problem because there's a way to get this problem into a setting for this problem which has an oracle that solves it. Yeah, and then the solution can be brought back into here being the solution for this guy. Easier done. Okay. So now I click on the slides. My presenter will work. All right. So the way to do this is first we're going to put in a referee, and the referee is going to give some X to Alice and some partial matching and W string to Bob. So we have the same setup as before. Okay. And now imagine that there was like some state psi X, depends on this X that Alice thinks. Yeah. And in addition, there was some projector. So it's an observable, but in particular, it's a projector, right? That depends on Bob's information and not Alice's. Yeah. I told you there's these two things that exist. And also, it's true that the trace of, or the expectation value of this projector with respect to this state psi X exactly equals 2 epsilon B. What would that mean if such a thing existed? Okay. I mean, for one, if Alice could somehow describe this state to Bob to a high enough accuracy that Bob could then use that description to compute expectation values with respect to observables, in particular with respect to this projector, then to within an additive error epsilon, then what Bob could do is estimate this quantity. And then he'd be able to see the difference between 2 epsilon and 0. Yeah, because he's got an epsilon accuracy estimate. And so in particular, we'll figure out what B is, thus solving this original task. Yeah. So now, like to kind of make things concrete, we need to be like, is there a state that does this? Is there a projector that does this? And make sure that the state doesn't depend on Bob's info and the projector doesn't depend on Alice's info. Turns out there is such a state and there is such a projector, right? Here is the state. I don't expect you to like absorb it, but note that it's got X's in it and it's got no I, J, K's in it and no W's in it. And this guy here, take my word for it, it's a projector. It depends on W, it depends on these IJs, but it does not depend on X's. Yeah, and you can even compute the rank of the state and everything behaves nicely. And so these things exist.
But these measurements, already be sure, these measurements will be then the measurements for your shadow estimation scheme, right?
Well, we're kind of showing that like the shadow estimation scheme embeds in it this problem. Right? And so if you could solve the shadow estimation scheme, then you could solve this problem.
Yeah,
so all the
I wanted to be sure that I'm
All right. So this kind of seems like it solves everything. So all Alice would need to do is like send a message that describes psi X. There's some technical issues with this because somehow for the lower bound, the communication lower bound of Levinsky et al. To apply, the procedure would have to be deterministic. That's why it's phrased in terms of a large fraction of instances as opposed to like the type probability. Whereas Alice's protocol for like describing some state to Bob in the setting of expectation values is all probabilistic measurements versus value probabilities. And so we need to like make the actual notions of success match before we can import the lower bound. And so there's this kind of need to de-randomize the procedure. And so the way we de-randomize this is we say, imagine if the referee gave this description X to Bob, to Alice, and Alice now has this state psi that she wants to describe. Instead of describing psi, I mean, instead of like doing something like classical shadows where you make many copies of psi and then you measure them, and then you see some probabilistic outcomes that you then communicate. She already knows the exact classical description. So she could in principle, if there's a procedure for actually doing classical shadows, she also knows what measurements to do, right? She could actually classically simulate the entire thing. Yeah, so she could imagine simulating S copies of psi being measured by some procedure, all classically. She could write down an exponential list of probabilities of seeing all these events, and then she could de-randomize. So she could choose the best outcomes that are most, communication, that have the most like bang for buck in terms of communication to Bob. And this gives us like a de-randomization procedure that really completes this reduction. If all of the details didn't make sense, like read the paper later.
But that's the Gossett paper.
Gossett used a reduction, but actually this reduction was in the Babinski et al. Paper as well. But we changed the reduction to like do this de-randomization and stuff like this. Yeah, there's like changes to it. And yeah, we put in epsilons and stuff. There were no epsilons in any of this. So this says now, given this reduction, what we're now saying is suppose that for any x, Alice can set an approximate classical description, this thing to Bob, such that for a high fraction of instances, Bob can estimate this thing to additive error. Suppose this was true, then necessarily the maximum length message must be bigger than this thing. Yeah. Okay, great. But
and how comes the embedding the big?
Yeah. We don't want to talk about lengths of messages. What we want to talk about is mutual information. How much information did Alice communicate to Bob about X? Yeah, that's what we want to talk about. So let's do a little crash course on info theory. It's going to be quick. I'm going to tell you what. Maybe I can skip this. Do people know what mutual information is?
No, I speak for myself. Yes.
Okay. Put up your hand if you know what mutual information is.
The shame method.
It's okay. Maybe I'll do it.
And you don't know this.
Okay, all right. I'm gonna do this super quick. Okay. So X is some random variable. It might have a distribution like this or anything in between. And the entropy of X is kind of a measure of the amount you don't know about X. If someone told you what the distribution is of X, right? But you're about to look at a sample, you don't know, like you might know the distribution, but you don't know what that sample is going to spit out. It's the amount of information you learn from looking at that sample. So in here, where the distribution is like, there's only one thing, X has to be 2. There's nothing you can learn from looking at X, a sample, right? Whereas here, where it's uniform, there's a lot you can learn. It could be any of these. So the information is like log B. So you can think of entropy as the amount you don't know about X. And then there's this conditional entropy thing, which is like, imagine if there was some random variable X and associated with it was some random variable Y. And somehow, if someone told you what Y is, the distribution of X changes, right? You know more about X or in principle. So you can think of this as a distribution of Y, and then someone tells you what X is, and then the distribution changes. So this is like measuring the amount of entropy in X when you know Y, but you average over all the possible Ys you might, with the probability that you would see those Ys. And so you can think of this as the amount you don't know about X when you know Y, averaged over all the Ys. And finally, we're at the end, the mutual information is the difference between these two quantities. So this is the amount you don't know about X, and this is the amount you don't know about X when you know Y. And so the difference is the amount you learned about X when you learn Y. Yeah. And this is symmetric, but it's not really in a symmetric form. But anyway, that's like a concept of what mutual information is. It's about common information between two variables. Okay, so we want to lower down this mutual information. So again, we have the same setup, but we have a referee who's going to generate uniformly some X that has been sent to Alice, some partial matching that has been sent to Bob, and he's also going to uniformly pick the B, which is like the answer that they have to figure out. Then he computes W such that the promise is satisfied. So it's easy to see that there's some W for every choice of X, X and B. All right, so once this is done, referee sends out the relevant data. And then we'll have this lemma. Suppose Bob can learn the secret B with high probability, then the mutual information is at least this amount. Okay, so this is what we want to show. This is what we mean by lifting this thing. So what we want to say is like the message has to somehow contain a bunch of information about X, at least a lot of information. So this is like before it was a lower bound about how long the message has to be. Well, the message could be really long, but not contain any information about X. So we really need it to contain information about something useful. Yeah. And so for this lower bound, I'm going to maybe go through this very quickly. I recall it was like the definition is like a difference of two things. But this piece here, the entropy of the message given X is 0 because we de-randomize the whole procedure. Yeah. And so the only thing that matters is the entropy of the message itself. We want to show that that's larger than this amount. And very quickly, what we do is, one of the things we do is like, you put it into like Huffman encoding, which is a kind of encoding that will preserve the entropy of the message, but it will make sure that the average length message is very close to the entropy of the message.
The variable length coding, right?
Yeah. And then what we do is we say, well, we're just going to fail on messages that are like too many multiples beyond the average length message. So if your message is like more than 10 times the average length message, we're just gonna, Alice is just gonna decide she's failing, she's not sending a message to Bob at all, right? And somehow we only pay a small failure cost for doing this. And in return, we make sure that the average, the maximum length message is not too high, right?
So in fact, I mean, this will not matter whatsoever except the prefactor, right? That's interesting.
Yeah, that's right. And then what this guarantees us is somehow the entropy is pretty close to the maximum length message now. It's only like a constant multiple away from the maximum length message, which then tells us that the mutual information must be lower bounded by this thing because the maximum length message was lower bounded by it. Yeah, up to some constant factors. And so now we have a lower bound on the mutual information. All right, and now we're in like real business. From here, it's like pretty standard lower bounding techniques, like information theory lower bounding techniques. So here is how it works. We're going to imagine before this whole circle was one Alice. Yeah, and we had this lower bound and we left the message, and now we have a lower bound in mutual information. But now we're going to split this into two things. So what we know before we even split it is that mutual information between this message and this X is at least some amount, right? But now in here, we say, imagine there's two Alice's. There's Alice1 and Alice2. Alice1 sees the X, prepares S copies of this state psi X, and then through a quantum channel sends them to Alice2. Alice2's job is to do the classical shadows thing, right? She's got to learn the state and then communicate it to Bob. Yeah. Right. And this is just the lower bound theory, the final lower bound theory we want to prove. And it goes like this. We know the mutual information is lower bounded by this amount. We just showed that in the last slide. Then by the data processing inequality, we're saying the mutual information, the information about X that Alice sends to Bob had to have come from this state that Alice had. Couldn't have come from any other way because that's all she got. And so the information she can access, it's called accessible information of this state, is more than the information that this message contains about X. Yeah, it's by the data processing inequality. Then Haleko tells us that accessible information has to be, like gives us an upper bound on accessible information. How much information can we extract from the state is given by the log of the dimension of the state. In general, this row tensor S is it can be many different things depending on the input X. And so there's some dimensions spanned by these things. And Haleko says that the log of this dimension has to be greater than the accessible information. And we can compute this quantity. And very conveniently, it depends on S, right? Because there's an S-fold product of rows. So it's like S times log B on epsilon, because that was the dimension of the rows in this embedding of these guys. So now we're in business, right? We say S is bigger, like S times something is bigger than the accessible information, which is bigger than the mutual information, which is bigger than this quantity. And that gives us a log nonetheless, right? So divide this guy by this prefactor, and we get S is bigger than this thing. And of course, we hide this log component in a tilde when we present it.
Does it matter what the image outcome of this observable of focus?
The Frobenius normal matters a lot.
Yeah, I mean, yeah. And I mean, burst is entering the.
Where does it enter? It enters in this B. So we had to choose, like we chose the number of bits in here to be B on epsilon because we were fiddling with the choice of the V in order to make sure that we got the lower bound we wanted. Like the lower bound was like square root V on epsilon or something, and we chose the V to be like we want the dimension to be as small as possible in terms of here, but at the same time we want to make sure that V is large enough that the observable will be handled. So I can't remember exactly where it comes in, but it's like it's related to these choices of like how you embed the partial magic problem into the problem. Thanks. No worries. All right. So open questions. So that these these first two are kind of very natural when they relate to what you raised earlier, which is like this split between pure and mixed and joint and independent. So we know in the joint and pure setting, that's our work here, and we have like matching upper and lower bounds. And we know in the independent and mixed setting, that's HKP and there's a matching upper and lower bounds, but we don't know how this split goes in these two other settings. And so it's kind of natural to say which one of these, or are they both necessary to get this speed up for this improvement?
Well, to be clear, but that helps, right? I mean, the jointness really comes in, as we explained, it comes in through purity, right? Otherwise,
yeah. But then you also need the purity to like for the upper bound to work. So
for the lower bound, you could probably.
Yeah, but the thing is, like for independent measurements, you expect a higher lower bound and in fact have one. So a lower bound for joint measurements is not valuable for independent measurements. So in principle, you need.
No, but I'm wondering, can you apply the same, like do the same reduction to get another lower bound that's higher, or?
It could be. We haven't actually thought about. Well, I mean, the thing is, there's no point because the lower bound from the independent setting already is saturated by the upper bound, so it's already matched. So we know that we can't improve the
mix, right?
Oh, but you mean in the yeah, it's possible. It's possible that we could like. I mean, certainly you could split this into two copies. One is like upper bounds, the other is lower bounds, and then try to fill these boxes.
I think we know a match the box.
Okay, aside from like these two, you could also say, can we find grain by rank, which is a kind of very natural thing when you look at tomography, right? In tomography, they already have these fine grains by rank.
So going to the table before, HKP doesn't also answer to the independent compute, the bounds.
No, because I mean, their lower bound applies. Their upper bound applies, yeah, but they can't be guaranteed that you couldn't do something faster if you're guaranteed the state is pure.
The worst case is given by a pure state, but lower bound, right?
No, the lower bound is given by a mixed state.
The upper bound.
Yeah. Okay, so fine graining is a natural question. The other one is like this extension to local observables. So, I've talked about shallow shadows to you guys before, which is like in between. Well, I mean, before we even get to that, I mean, HKP has this global procedure and they have this local procedure, right? C1 procedure. And our joint measurement setting is kind of analogous to this global. And you could say, is there a local analogous version of it? And it's not easy to define a local measurement that is somehow joint across all copies. It's a bit weird, but there are definitely ways you could kind of try to do this. And it's worth considering that extension.
Well, fine, but not very natural, right? I mean, why would you have like on-site measurement that for over many copies? I mean, if you have
I mean, the one reason is that there are actually observables for which the local procedure works better than the global one, right? Because the local procedure scales like to the weight of the observable, and the global scale is
No, of
like,
course, but it's really a
Minuscule.
tiny measurement. That's what I'm saying. But yeah.
yeah. So I mean, you could hope that maybe there's a procedure for the joint measurement setting that in the local setting actually performs
yeah.
better for these set of observables. I think there's another question.
Personal weekend.
Yeah.
Unfortunately.
All right. Even I have to one at some point.
Yeah.
Problem is
I'm
that
pretty much done.
you would blame on me. That's a good thing. That's a good thing, but in particular on the computer.
Extension of to these quasi-local observables, which is the thing we're doing in shallow shadows, and we kind of take this one step further. And finally, I'd say this like lower bound scaling in the number of observables. Right now, I mean, our upper bound can easily be lifted to something that scales the number of observables. It's like a log n, where n is the number of observables. But our lower bound wouldn't scale in that because you don't have like a analog of the.
And so your funny constraint of Pareto squared is really glued to that setting. So only then you get the up and lower bound being matching.
Yeah, I mean, for a single observable, we get upper bound and lower bound matching. If you try to say like what happens if you consider ensemble of observables, or like what happens even if you consider like a failure probability delta, how does it scale in failure probability delta? We don't like they start to diverge.
Okay.
Now.
Yeah.
Because the upper bound can be exponentially suppressed in the delta and the lower bound can't. It's for like constant delta.
But then you probably have to modify this communication problem, I guess, right? You have like a multi-people, blah blah.
Yeah, we've been looking at doing various tricks to have like we've actually looked at exactly that. Like
There's not multiple bobs now.
Multiple bobs kind of setting. A big problem with this is the lower bound that we inherit from the Levinsky et al. Is really crappy in the sense that it doesn't depend on failure probability. Like it's really poor on the failure probability, just like a half or something. And like you can change the failure probability a lot, and the lower bound doesn't change. And so yeah, it's hard to lift it. But it's like a kind of nice set of questions, and we're done. So celebrate. So, okay,
I'm not sharing.
Yeah, great. Thanks for the wonderful talk.
Thanks for the talk. I'm still really uncomfortable about this meeting business. Like,
it literally does not matter. It's like the least important
Yeah,
thing in the whole
say,
talk. And I try to like do this every talk, but people love the meaning of means.
no, I mean, like, I really don't understand physically, like, why you would prefer to use the median rather than the
Oh, okay. I can give you a nice introduction to this, right? I can give you a nice introduction to this. Imagine, like, you're talking about the failure, like the probability of failure of a procedure that you're doing, right? So, like, you're estimating some number, and you're like, what is the probability that this number is like really bad as an estimate? Yeah. If you had a bunch of them, right, and you're like, the median's going to fail. For the median to fail, like all of the ones above it have to fail, all of the ones below it have to fail, right? But there's a whole bunch of them, all independent, right? So for each of them to fail, somehow you get a power, like the failure probability has to, like they all have to independently fail, right? And there's like 10 of them that all independently fail. So it's like failure probability to the power of 10 for this median and means thing to fail. Whereas for the average,
I recommend a nice review on this, which we had to look up for this paper with Jonas, with Amsterdam Jonas. So there's a good readable review on median and means.
Yeah. That would be helpful.
Can I make a practical proposal? Can I turn this talk from a hybrid talk to an on-site talk?
absolutely.
Thanking Hakop again for this wonderful talk.